Hello and welcome to Remote Chemistry Teaching by Dr. John Petty. We're going to pick up more or less where we left off when we were regularly holding classes. That is, we've just finished talking about electron configuration, the arrangements of the electrons and where they are in the atoms. We need to know about electron configurations because, of course, the electrons are what actually do chemistry. Whenever you're talking about a chemical reaction, you're talking about rearranging what the electrons are doing in some fashion. Which means we have to start talking about bonding. Bonding is what changes a mixture of the elements into compounds. Basically, we run into two different kinds of compounds, molecular and ionic. The difference between the two is in fact basically a question of what kind of bonding they have holding the atoms together. To help us visualize what's going on and understanding the bonding and where the electrons are going and what they're doing, we're going to make use of what are known as Lewis Dot structures. In a Lewis Dot structure, you simply start out with the symbol for the element and then use a dot to represent the valence s and p electrons around that atom. So for sodium, you'd have one dot, and it doesn't matter which corner you put the dot at. For magnesium, you have two, and the two electrons obey Hund's rule, that is, they spread out. And again, it doesn't matter where you put them around the magnesium. Boron has 3 electrons, carbon has 4 electrons, and then it brings us to nitrogen. And on nitrogen, we finally have a pair, and they, of course, follow Pauli's rules that you can't put more than 2 electrons together in an orbital. Oxygen has 2 pairs, fluorine has 3 pairs, and that brings us to neon, which has 4 pairs of electrons surrounded in its valence shell, which is 8, which gives rise to what is known in chemistry as the octet rule. The octet rule, simply stated, says that the elements of the main group, which are columns 1 and 2, 13 through 18, on the periodic table, will in fact try and react so that they end up with the same number of valence electrons as the closest noble gas. We see for simple ionic compounds that the octet rule gives fairly simple and straightforward results. We know from our discussion of electron configuration that the alkali metals, the alkaline earths, and the elements in column 13 of the periodic table have 1, 2, or 3 more valence electrons than the last noble gas. And therefore we see these metals, when they react, they have the tendency to give away those outermost electrons and form respectively +1, +2, and +3 cations in their compounds. On the other end of the table, in columns 16 and 17, we have the nonmetals. And the nonmetals are 1 or 2 electrons short of a noble gas count. And therefore they are not interested in losing electrons, since that would in fact take them further away from a noble gas. Instead, we see those elements try and form anions. That is, they try and gain 1, 2, or 3, if they're in column 15, electrons. So they get to the next noble gas, not the last noble gas. The transition metals, on the other hand, are in a very different category. They are not 1 or 2 electrons away from a noble gas count. They tend to be 6 or 7 or 10 or 12 electrons away from a noble gas count. So the transition metals are going to be doing something different when they are losing electrons. They have something else. And we'll eventually get around to talking about those ions. I also have a problem for the elements in columns 14 and 15. They are not just 1 or 2 electrons away. They tend to be, again, 3 or 4 or more electrons away. And so what they're going to have to do to reach their noble gas counts is going to be something different. They're not going to form ions. They're going to tend to form molecular compounds. So let's see how the octet rule works for the simple case. of the ionic compounds. Therefore, we see in the simple case where you have sodium and chlorine, the sodium has one valence electron and one dot, whereas the chlorine has 7 valence electrons and 7 dots. And as a result, the one dot on the sodium is transferred to the chlorine, which gets it its 8 and would be an argon configuration, whereas the sodium is dropping back to neon for its noble gas count. And we end up with one cation and one anion, and so we have sodium chloride. For calcium and fluorine, on the other hand, the calcium has to lose 2 electrons to get back to its noble gas count, whereas the fluorine only wants to pick up 1 electron to get to its 8, and so we have to have 2 fluorines for every calcium to run this reaction, because we have to have the same number of electrons gained and lost. And so the compound calcium fluoride includes 2 fluorines for each calcium. It's a little more complicated for aluminum and sulfur. The aluminum starts out with 3 electrons, and it wants to lose all 3 of them to get back to neon for its noble gas count. The sulfur wants to gain electrons. In fact, it wants to gain 2 electrons, which gets it to its argon count. But the aluminum's only giving away 3. The sulfurs are only picking up 2. And so we're going to actually have to have several of everybody if we're going to end up getting this to balance out right. The first number that includes both 3 and 2 is 6. And so we're going to have 2 aluminum atoms react, so they give away 6 electrons. And we're going to have 3 sulfur atoms react so that they can pick up the 6 electrons. And so aluminum sulfide includes 2 aluminum atoms and 3 sulfur atoms. And so we see the case for metals and nonmetals is to be fairly simple. The metals have a tendency to lose electrons, the nonmetals gain them. The metals become cations, the nonmetals become anions. The ions are attracted to each other by their coulombic attraction, and so we end up with compounds. And that's fairly simple and straightforward. It becomes more complicated if we start bonding nonmetals with nonmetals, because the nonmetals don't like giving away electrons, and so there's nobody who's willing to become the cation. And in this case, if they're going to end up getting more electrons, they're not going to be able to do it by taking each other away. They're going to have to do it by sharing. We start talking about covalent bonding. And that's the subject of the next video, which you are to see. That's all for the moment. Thank you.